Hi everybody. Today I'm going to talk to you about the last of Newton's laws of motion. That's Newton's third law of motion. And I think it's the one that makes everything understandable. It's the one that takes the idea of a force and the idea of mass, kind of puts them together into a method that explains a lot of the way things move in the real world. So we're going to talk about that real quickly today. And then one of the most important things is we're going to try to address one big misconception. So keep an eye on that as we go through this. Okay, Newton's third law of motion, you probably learned in middle school, says for every force there's an equal but opposite reaction force. That's a perfectly fine way to understand it, but it omits a lot of problems, a lot of sticky areas that people don't understand, and so it causes misconceptions. And so here's how I like to write it. It's more wordy, it's not as memorable, I get it, but it is one of those things where if you put in the extra information and you learn it the right way, you won't have many problems applying it later on when you are forced to in situations and problems, things like that. So here it is. So let's take a look. For every force that object A applies to object B, okay, now you see I'm making it specific. Okay, so object A is applying a force to object B. What happens? There is a reaction force that object B applies back to object A that is equal in size and opposite in direction. So let's take a look at a couple of situations here. First off, let's imagine this is you right here, this little red guy, and then this blue box is in your way, and you'd like to move it. So you walk up to the box, you put your hands on the box, and you apply a force. So this is your applied force right here. So you are pushing the box in this direction right there. Okay, so far everything's good. We could use Newton's second law and the mass of the box to be able to figure out how much acceleration you produce. We could use vector addition if we knew what the friction forces were to analyze if this action force actually even produced any acceleration. We could do all sorts of different things. But one of the things we haven't talked about yet is the fact that if we're looking just at you, not at the box anymore, all of a sudden now there's a reaction force that's acting on you. If not, then you would sort of move right through that box. You would just push that right along. So you're applying this action force in red, and the box applies a reaction force back on you that I've drawn in blue. And notice that the length of this vector and the length of this vector are the same, but notice that they're in opposite directions. And notice that one force applies to the box, that's yours, and one force applies to you, that's the box's. Does that make sense? I hope so. This is where a lot of people run into problems. So please be careful with it and make sure you understand that when you apply a force, then there's a force applied back to you. If you understand it, then it makes a lot of normal motion in everyday life much more comprehensible. Like, for example, here's you walking. Okay, I want you to really think about what you do when you walk, right? So your leg, your foot, pushes backward on the ground. Okay, so here's your foot. You are applying a backward force to the ground. So I've drawn that on the ground as your action force right there. But the result of that is that you move forward. How on earth could you apply a force backward and get yourself to move forward? Remember that any change in motion must occur as a result of a net force. And so you must have some sort of net force acting on you that pushes you forward, that gets you moving in the forward direction. You pushed backward on the earth, or on the ground, or on the floor, or whatever, but you moved forward. And so understanding what a force is and how it produces an acceleration from Newton's second law, we know that there has to be some force on you. And that force on you is the reaction force. And here's why. So come over here for just a second, and you can check out this comment here in blue. So imagine the inertia of the Earth. Okay, well, let's not even take the whole Earth. Let's just take this little section of the Earth right here. It's got a huge amount of mass, so it's really resisting a change in its motion. You've applied a force to it, but it's really, really resisting it. Could you accelerate it? Sure, a little bit. By a little bit, I mean a lot, very, very small amount, but you could accelerate it just slightly. On the other hand, um, it's resisting that change in motion. And so as you push, you really feel that action or the reaction force applied to you. And that's this action force is causing, along with the inertia of the Earth, the reaction force. So this action force plus the resistance is causing the reaction. That's why you get that. If you push on a wall and the wall doesn't break through, then it applies a reaction force back on you and you may fly backwards. If you do push-ups, you push on the floor, but you can't push the floor down. I'm not strong enough to push the floor down. So as a result, I end up moving upward. And that's because of the reaction force. Same thing happens with rockets. And so a lot of times people will memorize this as if it was a rule that applied to rockets only. But in reality, it applies to just about everything. A rocket pushes exhaust gases out the back. Conventional chemical rocket does this. It pushes exhaust gases out the back. And so this gas, this body of gas right here, is getting a push by the rocket outward, backward. And then the gas, as a result, because it's resisting that change in its motion, is also going to apply a force on the rocket forward. And we know that they are the same size, and we know that they are in opposite directions. So super handy to have this action-reaction force. In fact, as you see, they go together. It's important to remember that as a pair, we could either call them a force pair, which you will see fairly often, force pair, or what I prefer, an interaction. So one interaction is really made up of an action and a reaction force pair. So you can see how this works. So there's this, they're interacting, these two objects are interacting, and they have one force, action force, and one reaction force. Same thing with you and the ground. You're interacting through a action force and a reaction force. Same thing with the rocket and the exhaust gas. They're interacting with an action force and a reaction force. Notice the misconception here is that people believe if you just memorize for every force there's an equal but opposite reaction force, it sounds great. It sounds exactly like what I just talked about, but there's no mention of the fact that they have to act on different objects. They must act on different objects. I can't stress that enough. The classic description of this is the horse and the cart problem. So let's imagine you've got a horse, and it's a really smart horse. Yep, he knows physics. And so you hook him up to, or he thinks he knows physics, let's put it that way. You hook him up to a cart, and he says, oh, okay, well, I'm going to apply a force to the cart, like so. Okay, and that's going to be the action force. I'm going to pull that cart forward. But because the cart is going to resist, the reaction force right here is going to be on the horse. Now let me ask you a question. Are these two things connected together some way? Yes, they are. So if you have an action force going in one direction and a reaction force going in the opposite direction, and they have the same size, but they're connected together, doesn't that mean they're going to cancel out and the horse is not going to go anywhere? So this horse decides not to move, right? Silly, I know. It's a goofy situation. But this is kind of a famous physics problem. It's called a paradox, but it's not really a paradox because you're thinking about it the wrong way. Okay, so yes, those things occur, but the real reason why things move is not because of that the horse is pulling on the cart. You need to think about the horse and the cart being the one object. Okay, those are both what we would call internal forces. Internal forces always cancel. You can't have a sailboat and then have a fan in the sailboat blowing the sail and get the sailboat to move anywhere. It just doesn't work. Those are both internal forces. So you have to have something external to get something to move. And so let's talk about that for a second. So now instead of thinking about the horse as one thing and the cart as a different thing, let's think about the horse and cart as one thing. Now the horse applies a force in this direction. That's the action force. the horse's hooves push backward on the ground. And so the horse and the cart together experience the reaction force. And so the reaction force is what moves the cart and the horse forward. Again, we know that the horse and the cart are going to have equal but opposite internal forces. What that means is not that they're not going to move with respect to the ground. It means that they're not going to move with respect to each other. And so that's kind of important, right? That's good. You don't want the cart to slam into the back end of the horse, or the horse to run off and the cart to be left behind. You want them to stay in the same relative positions. That's good. So really, the reason why it moves is this action and reaction force with the horse and the ground, not with the horse and the cart. So it's a kind of one of those misconceptions. We're going to practice this quite a bit for the last week of the unit, and then we've got our test coming up. So make sure you're ready for that. If you have any questions with this, please let me know. Thanks for watching.